Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. This is the fourth in a series of short videos on basic electronic circuit analysis. So far I've covered Ohm's law, Kirchhoff's current law, and Kirchhoff's voltage law. In this video, I want to cover the sleight of hand that helps unravel circuit analysis in certain situations. It's called Thevenin's theorem, which gives us the Thevenin's equivalent circuit. Now, Thevenin was a French telegraph engineer in the 19th century, and his theorem was released in 1883. Now, if you find this video helpful, please click on the like and subscribe so that you will be notified when new videos come out. So what does Thevenin's theorem tell us? Well, hang on, this is going to be a little confusing, but here's what it says. For any linear electrical network containing only voltage sources, current sources, and resistances, it can be replaced at terminals A and B by an equivalent combination of a singular voltage source with a voltage V sub TH in series connection with a equivalent resistance of R sub TH. And we get R sub TH by shorting all voltage sources and opening all current sources and then calculating the remaining resistance value. We get the voltage VTH by calculating the voltage at terminals A and B with them open circuited. Now, are you confused? Well, I don't blame you. I certainly was really confused by this the first time I heard it. Well, let's see if we can unravel it at the whiteboard. All right, here we are, Thevenin's theorem. Another one of those sleight of hand tricks that we use in order to analyze a circuit and to break it down into something a lot more manageable. We're going to start with this representative circuit that we're going to be using to demonstrate Thevenin's theorem. It consists of a voltage source over here, like a battery, and we're assigning it a value of 50 volts. We have a resistor in series with that of 15 ohms. We have a current source here of 2.5 amps. We have a resistor in parallel with the current source here of 5 ohms. And then we have a resistor up here, 60 ohms, coming out to points A and B, which is where our load resistance is, RL. And in reality, this could be a whole big circuit out here, but it's all represented by a single entity here, RL. And so the question that we're looking to answer is, what is the current through this resistor? Well, using Kirchhoff's voltage law and Kirchhoff's current law and Ohm's law and all of that stuff, we could write a series of equations and solve them simultaneously and eventually figure this out. But Thevenin's theorem allows us to do it a lot more easily and a lot more quickly. So, how do we do that? Step one, we disconnect RL from everything. Remember, Thevenin's theorem requires A and B to be an open circuit. So that's the first thing we're going to do. We're going to disconnect our load resistor here. Step two, we replace all of the voltage sources with a short and all of the current sources with an open. Now, this doesn't make a lot of sense to us, but this is what Thevenin's theorem says. So we're going to come over here. We're going to disconnect our voltage source, and we're going to place a short in here instead. We're going to disconnect the current source, so there's no way that this current source can contribute anything. And this is what we're left with. Step three, we calculate the equivalent resistance of what's left. Well, R1 here is in parallel with R3. So we have R1 in parallel with R3. Well, from standard resistor stuff, we know that 15 times 5 divided by 15 plus 5 is the equivalent resistance. So it's R1 times R3 divided by R1 plus R3, and that value comes out to be 3.75 ohms. There we go. So that's this. Now, this parallel combination of R1, R3, remember that what we're doing is we're looking in from A and B in at this, what's left here. So we've already calculated these. These are in parallel with one another. But looking in from this direction, we're looking in through this 60 ohm resistor to this parallel combination and back to B. So what that means is that this 60 ohm resistor is in series with this parallel combination. So the equivalent resistance looking in this way, or R Thevenin, is equal to R2 plus the parallel combination of R1 and R3, which gives us 60 ohms, which is R2, plus, we already calculated this at 3.75 ohms, which means that R Thevenin is equal to 63.75 ohms. All right, cool. So we got that. That is step number 3. Okay, so let's take a look at step number 4. We go back to the original circuit. So we have to take out our short here. Let's take our short out. And we have to connect up our voltage, connect up our current. But we still leave the resistance, the load resistor, out of the circuit because, again, Thevenin's theorem requires A and B to be an open circuit. So, we are going to apply Kirchhoff's current law, or nodal analysis, to this circuit. And so we're going to label the point just after R1 and before R2 as the point C. This is node C. So this whole section is node C. The current coming from the current source here is I1. The current coming from the voltage source through R1 is to node C. We're going to call that I2. And the current going toward the junction of R3, here, we're going to call that I3. Now, because this is an open circuit, there isn't any current coming out this way, so we don't have to worry about that one. Now, according to KCL, Kirchhoff's current law, I1 plus I2 plus I3 is equal to 0. Now, I3 is negative. Why? Because it's exiting the node. So we know that I3 is a negative current. We know I2 is positive because it's going into the node. So I2 is a positive current. And I1 is going into the node, and so it also is a positive current. And we know that this I1, this is I1 here, this I1 is 2.5 amps. Now, we need to apply Ohm's law for these other ones. Well, I2 is the current going through resistor R1. According to Ohm's law, remember, the current is going to be equal to the voltage across the resistor divided by the resistance. Well, what is the voltage across the resistor? Well, the voltage across the resistor is the source voltage minus the voltage over here. So I2, we have the voltage here minus the voltage here divided by the resistance R3. So that is the current coming in from that direction. So I3 here is the voltage, again, Ohm's law, the voltage across the resistor, which is VC, divided by the resistance R3. Now let's put it back into our KCL. So it's I1, which we know is 2.5 amps, plus I2, which is V1 minus V at C divided by R1. Now I3 is negative. So we're going to stick out here minus the voltage across this VC divided by R3. And we know that this has to be equal to 0. Oh, I'm off screen entirely. We know that this has to be equal to 0 because Kirchhoff's current law. All right, there we go. So I1 is 2.5. V1 is 50. We don't know VC. We know R1 is 15. Minus VC, which we don't know yet, divided by R3, which is 5, equals 0. Now we want to get rid of this stuff down here. So what we're going to do is we're going to multiply both sides of this equation by the same number. We're going to multiply both sides by 15. So we have 15 times 2.5 plus 15 times 50 minus VC over 15 minus 15 times VC over 5 is equal to 0 times 15. Well, 0 times 15, that's an easy one. That's 0. 15 times 2.5 is 37.5. We have 15 divided by 15 here, so that's a 1. So now we say plus 50 minus VC. Here we have 15 divided by 5, that's a 3, minus 3 VC is equal to 0. We gather like terms. We have 37.5 plus 50 gives us 87.5. We have minus VC minus 3 VC, that gives us minus 4 VC is equal to 0. We add 4 VC to both sides. So you have 87.5 minus 4 VC plus 4 VC. That gets rid of it on this side, but then it puts it over on this side because 0 plus 4 VC. We have 87.5 is equal to 4 VC. So 87.5 divided by 4 is equal to the voltage at C. in this case, which comes out to be 21.875 volts. Now there's no current through here, so the voltage at A is going to be the same as the voltage at C. So that means that our Thevenin voltage, V Thevenin, up here is equal to 21.875 volts. All right, now that we know what that voltage is here, we can connect our load resistor back up. And what we essentially have at this point with this is we have a voltage source of 21.875 volts with a series resistor of 63.75 ohms. Here's our point A, point B, and our load resistor here of 50 ohms. Now it's easy to calculate the current through our load resistor. We have 21.875 ohms being applied through this combination of series resistance. So the current through the load resistor is equal to 21.875 divided by this series, so that's 63.75 ohms plus 50 ohms. We have 21.875 divided by 113.75 ohms. You do the math, and this comes out to 0.1923 amps. So I sub RL is equal to this. And then we can calculate the voltage across this point, because now we know the current V sub RL is equal to the resistance RL, which is 50, times the current through RL, which is 0.1923. So the voltage across RL would be equal to 9.615 volts. So now we know the voltage that is here in this circuit is going to be 9.615 volts. We know the current going through that is 0.1923. So let's make a note of that up here. And we're going to go back and check our work. So IRL is equal to 0.1923. VRL is equal to 9.615 volts. Now let's go back and check our work, because that kind of proves whether we did it right. Well, we know the voltage across here is 9.615. We know the current through here is 0.1923. Now, that means that if the current through this resistor is 0.1923, because these are in series, that means that the current through this resistor also has to be 0.1923 amps. So that means that we can calculate the voltage across R2 because we know the current, 0.1923, and we know the resistance, 60 ohms. So knowing those two quantities, we know that VR2 is going to be equal to 11.538 volts. What did I say? 538. So we know the voltage across this resistor. We know the voltage at this point right here. We know that is this voltage there, right? So that means that the voltage at this point is equal to the voltage at this point plus the voltage across R2. So V at C is going to equal the voltage at A, 9.615, and it's, as we're going this direction, it's going up. So the voltage across R2 is going to go up by this. So we're going to add 11.538. And that gives us 20, oh, come on, Ralph. That's supposed to be a 2. 21.153 volts. That's the voltage at this point. Now, if we know the voltage at this point is 21.153 volts, we can now calculate, because that's across R3, we can calculate the current through I3. I3 is equal to this voltage because it's across the resistor. And we're going to divide it by the 5 ohms. So I3 works out to be 4.2306 amps. All right, so we have 2.5 amps coming from into that node from here. We have current going through here. We have current going through here. So the total current I3, this is IR3. The total current I3 is going to be equal to IR3 plus IR2, which is equal to 4.2306 plus 0.1923. So the total current going through there comes out to 4.4229 amps. That's I3, because that's IR3, which is this, plus IR2, which is that, comes out that. Now we want to work. Here we have 2.5 amps coming in, which is contributing to this. So I2, again, Kirchhoff's current law, I2 plus I1 equals I3. So that means that I2 must equal I3, 4.4229 229 minus I1, which is 2.5 amps, which gives us 1.9229, excuse me, it gives us, 1.9229 amps through R1. All right, now we know the current through R1. If we know the current through R1, we can calculate the voltage across R1. Again, Ohm's law. Ohm's law says V equals IR. So we take 1.9229, so VR1 is equal to 1.9229, which is the current through R1. I'll write that so it's legible here. 1.9229, and we're going to multiply that by the resistance, which is 15. So VR1 is equal to 28.8435 volts. You say, okay, great. But if we know the voltage across R1 and we know the voltage at C, we now can calculate this voltage out here. So, so the voltage here, V1, is going to equal the voltage at C plus the voltage across R1. Well, what's the voltage at C? We had that here. 21.153 is the voltage at C. We're going to add to that 28.8435. Doing quick math here. 5, 6, 9, 9, 9, 4. 49.9965 volts. And what is it? What did we start out with? 50 volts. And so that shows that Thevenin's theorem works. And like I said before, the good news is that RL can represent anything out here. And this can be applied time and time again, slicing up a circuit along the way. So there's the mess, along with all of the checking and moving back through it. So remember, the first step is you disconnect this here. Then you replace your voltage sources with a short and your current sources with an open. And then as you're looking in from A and B, you calculate the equivalent resistance of what's left over here. Leaving RL, and that's R Thevenin, leaving RL disconnected, you reconnect your current sources, you take the short out and reconnect your voltage sources, calculate the open circuit voltage at A and B, and that becomes voltage Thevenin. And that whole mess of a circuit becomes a voltage source with a resistor in series with it, R Thevenin, V Thevenin, and that's Thevenin's theorem. So there you have the short and sweet of Thevenin's theorem, which gives us the Thevenin equivalent circuit. This can really help us break down a very complex circuit. It's one of those circuit analysis tricks that we may not really understand why it works. We just do it because, well, it does work. In the next video, I'm going to talk about its companion, the Norton equivalent. If you find this video helpful, please be sure to click on like and subscribe to the channel. In the meanwhile, thank you so much for watching. Until next time, toodaloots.